Hello everyone. So in the last lecture we have started dealing with distribution factor. Okay, KD. We had discussed pitch factor. So this KD we were telling about phase spread, and then phase belt. We discussed about it. I hope if you don't remember, just we will revise it again. We talked about that there was the rating of a machine that was a three-phase machine having 18 slots, and three-phase two-pole machine was there, and there was two-pole 18 slots machine. So slots per pole will be 9 slots. Okay, slot per pole, that means 18 by 2, and slots per pole per phase will be 3, right? So we discussed about that, and then there was one more term, that is your slot angle. Slot angle was decided by 180-degree divide slot per pole, and that was, if you put this value, that it will be 20-degree, right? So this was our whole discussion there, and then we talked about the phase spread and phase belt. Phase belt generally refers to slots per pole per phase. So this is nothing but slots per pole per phase, and that was represented by M. And this phase belt was slot per pole per phase, and this phase spread was M into gamma. That was number of slot phase belt into slot angle. So that is 3 into 20. So I'm just generalizing it, okay, because this is a general construction of a machine, and it was 60-degree. Then we talked about various types of machine. For a single phase machine, we have a phase spread of, for any machine, if you say have single phase machine, then the phase spread will be 180 by 1, and then for a two-phase machine the phase spread will be 180 by 2, and similarly for any phase machine, if you have to find out the phase spread, 180 by 3. Okay, then this till here we have lasted. Now let's discuss what are the different types of windings we are able to do. So generally, if you have if you don't revise it, just revise it. Okay, that will be beneficial for you, because the upcoming things will be difficult if you don't analyze things. I hope it should be better if you analyze things. Now here, let us do some winding constructions here. So there will be two types of winding we will be considering, that is your concentrated winding, and then distributed winding. Okay, distributed winding. So as you can see here, slots per pole means in one pole there will be 9 slots. So 9 slots, that means 9 conductor. So if you can see here, suppose I am putting it as north pole, and this is a south pole of a machine, and here if you see, the total number of slots will be, total number of conductor will be 1 to 9. Okay, you can count it down, and then there will be from 10, it starts and it ends at 18. Okay, so this is the total number of winding. So in one slots per pole, that is your 9 slots. Okay, and then slot per pole per phase is 3. So I have already told you that this 3 will be representing R phase. Then this 3 will be representing Y phase, and this 3 will be representing B phase. Okay, these 3, B phase. So this is how the winding goes on. So each phase has this. Okay, Now, what I am doing, I am going to construct one distributed winding. I'm not going, I will discuss this concentrated winding. Distributed means winding is distributed in all the areas. Okay. So distributed winding, here what I will do, I will take the output of one of the phase like this, of R phase like this, and then I'll take this and it goes to the first of it. Okay. 10th, the conductor of 10th. Okay. From here again, it goes to second of this. Okay, this is number 2, number 2, number 3. This will be 11 and 12. Okay, so this is the whole winding. Now it goes to 2, and then from 2 again we take out the output and then we put it to 3, to 11. Okay, from 11 again we put it to 3. From 11 we take out and we put it to 3. From 3 again I take it out and put it to 12. Okay, and from 12 we take it out. So this is my R phase winding, and that is distributed in first 3 slots. Okay, R phase winding in first 3 slots per pole per phase, and having each slots have an angle of 20 degree. Each slots have an angle of 20 degrees. So 3 slots will have an angle of 60 degree, right? So this is our 60-degree phase spread is 60 degree, phase belt is 3. So this is how the distributed winding is done. Okay. Now, next is concentrated winding. Concentrated. See here, the EMF will be induced. If you see here, EMF will be induced in 3 windings. The R phase EMF, that is your R phase EMF, will have EMF in 1, okay, EMF in 2, and EMF in 3. So this is the whole EMF, the voltage induced in R phase that will be having EMF in 1, 2, and 3. Okay. Now if we want to note down how much resultant EMF is there. So EMF 1, if EMF 1 is considered in this is my EMF 1. Okay, EMF 1 having a vector that is your 0 angle. Now EMF 2 is phase displaced or space displaced by 20 degree, right? EMF 2 is space displaced by 20 degree. So this is the second EMF that has a displacement of 20 degree. This is 20 degree. Okay, and then the third EMF 3 is space displaced by EMF 2 by another 20 degree, right? So this will be like this. So whole and soul, if you have this EMF 3, EMF 2, and whole and soul, if you see the EMF, that is the resultant, that is R resultant, that has a phase shift of 60 degree. So this is how the EMF of the resultant, the distributed winding is calculated here. Okay. Now, the next phase, next is your uh, concentrated winding. Now, all the windings will be now concentrated in one. That is what concentrated words mean. Concentrated means all the windings of phase will be calculated from one phase only. Now here, what I will do, I will this, as you know, the phase spread and phase belt. Here, the phase belt will be always 1. For concentrated, phase belt will be always m equal to 1. Okay, so m equal to 1, that means I will always consider 1. Slots per pole per phase will be 1 for concentrated winding. Okay, so what I will do, I will take this first. This is one of this is EMF 1, and this is 2, and this is 3, and this will be 9, and this will be 10. So what I will do, I will take this winding from 1, conductor 1, and then I put it to 10. I take out from uh, 10, and again I will put it to 1. Okay, so I will take out the output. First let me take out the output. Okay, so this is my output, first turn output. This is my output of R phase. Now I entered and I put it like this. Okay, now next I will as my slot per pole per phase is 1, I won't go into 2. Okay, I'll go only directly to 1. Again the second winding will again go from here. Again it will follow this thing, and again it goes through the same path, and again this same. Again the third EMF will be on the same. So all the three EMF will be on the same conductor, right? And from the third, if I take out, this is my output. This is my output of R phase. This is my output. So all the three EMF is concentrated the on the conductor 1. So the resultant EMF will be, no, this all the three will be in same phase, that is E1, E2 and E3, will all the EMF is on the same conductor. And what happens, all the three EMF has the same phase shift. Okay, phase displacement, that is what the EMF, the resultant EMF will be 3. Okay, so this is here what happens here. If you see, there is a vector addition. There is a vector addition here in your distributed winding, but in your concentrated winding you have arithmetic addition, because all the thing is in the same phase. That is the difference here. Now what does the KD means? Let us discuss what is KD means. This KD, that is your distribution factor. It is also called as spread factor. You can write it down. Distribution factor, spread factor, spread factor, and then you have belt factor, and then you have breadth factor, breadth, breath. Okay, breadth factor. So all the names will be of the same. So this KD is nothing but the EMF induced in in EMF induced in distributed winding upon EMF induced in concentrated winding. Okay, so this is the whole picture. Or EMF induced by the vector sum to EMF induced by the this is the vector sum by arithmetic sum. Okay, so this is the whole. In the next lecture we will discuss about the calculation. Okay, I hope it is clear.